Welcome to Physicasts, physics podcast for 14 to 19 year olds. All of our podcasts are available on www.physicasts.co.uk. To get the most out of this podcast, if you're watching the video and you see the pause icon, or if you're listening to audio and you hear me say pause, have a go at the activity, and then when you've had a really good think about it, unpause it to find out what the answer is. GCSE Core Science, Episode 3, Energy is Useful. Today's episode is going to take you on a tour of the different forms that energy can take. You're going to learn about how energy can be transferred. You're going to discover what forms of energy are useful in our lives and what forms of energy are just simply a waste. You're going to be able to do some calculations to work out how efficient a machine is at converting its input energy into energy that we can take and use and be useful in our lives. And finally, you're going to learn how to use a Sankey diagram, a way of showing how energy is transferred from one form into another. So to kick us off, I'd like you to pause the podcast and write down the 9 forms that energy can take. You probably covered this last year, so have a think about all the different ways that energy can exist. Write them down. If you've got all of them, then you should have 9. Right, okay, now that you've written those down, let's have a look at what the 9 forms of energy are. So the first one in my list is electrical energy. That's the energy that is in an electrical circuit, and we use that energy to power things like lights, heating, electrical devices like TVs, computers, and so on in our homes. It's probably the most important form of energy at the moment in terms of being able to live a modern life. So if we didn't have electrical energy, we wouldn't have a lot of the gadgets that you're probably even watching or listening to this podcast on right now. The second one is elastic potential. Potential is a word which means that energy is stored in some way. So if we're going to store elastic potential energy, then we need to store that shape, and then when you let go, it returns back to its original shape. So by pulling on a rubber band, you are storing energy up in the rubber band. When you let go of the rubber band, then that energy gets converted into a different form, and that stored energy is what allows it to be able to move through the room. Number 3 is gravitational potential. What did potential mean again? That's right, potential is stored energy. So gravitational potential is where you store energy in an item by lifting it in a gravitational field, such as the one that's surrounding our planet right now. So if you take an object, pick it up, lift it high in the air, then you're storing in it gravitational potential. If you lift that object even higher, then you're going to give it even more potential energy. If the object's really big, then that will also store more gravitational potential than an object which is smaller. Number 4 is chemical potential. Chemical potential is another form of stored energy, this time stored in chemical bonds. So anything that you use where you burn or react a chemical and it gives out energy, the energy starts off as chemical potential. Number 5 is kinetic energy, the energy that we have in movement. Things that are very heavy have a lot of kinetic energy. Things that go very quickly also have a lot of kinetic energy. So something that would have a huge amount of kinetic energy would be a train going very quickly. Number 6, nuclear energy is energy which is stored in the nucleus of an atom. We harness nuclear energy in nuclear power stations and take advantage of this to release huge amounts of energy, much more than we're able to use in chemical energy. This is why nuclear power stations, while they've got their problems, are really good ways of producing large amounts of energy on a national scale, because a lot of energy is stored within the nucleus of an atom. Number 7, thermal energy. We covered that in episode 1. We said that thermal meant heat. Anything that is hot is giving out thermal energy in the form of infrared radiation. Number 8, light is a part of the electromagnetic spectrum, and it's in the same family that infrared radiation is in. Light is just a slightly different wavelength to thermal energy, and it's of course the part of the spectrum that we're able to see. It's still just transfer of energy though. Finally, our 9th one is sound energy, which really is almost a form of kinetic energy. As I'm speaking to you right now, that sound is being transferred by the vibration of particles back and forth in the air. So sound can only travel if there's a medium for it to travel through, such as a gas or a liquid or a solid. So right now, air particles are moving because I am speaking and applying pressure to the air. That energy of movement is what you hear as sound. Okay, so we've got 9 different types of energy, and we can convert one form of energy into another. But there is a rule in the universe that tells us how this can be done. It's called the law of conservation of energy. And the law of conservation of energy tells us that energy can neither be created nor destroyed. That means however much energy there is in the universe right now, there will be that same total amount of energy in the universe in 10 minutes time, in 2 years time, in 100 years time, and so on. So the only way we can move energy about is by transferring it from one place to another and from one type of energy into another. So for example, chemical potential energy stored in a fuel such as wood or coal can be turned into thermal energy when that fuel burns and releases heat. However, we can't create any more thermal energy than the amount of chemical potential energy we had in the first place. If our fuel was a perfect fuel, then all of that chemical potential would be converted into thermal energy. However, that's not how it works in real life. In real life, things are not efficient, they're inefficient, and not all of the energy gets converted from one form into another. Usually energy gets converted from one form into several different forms, and only one of those forms of energy is often useful to us. I'm now going to take you through a series of things that are useful to us in modern life, and I'd like you to identify which forms of energy this thing releases and which of these are useful to us and which of those are wasted. So to give you an example, if you're listening to this podcast on an MP3 player right now, then what is the useful form of energy there from our list of 9 types of energy? What is the point of the MP3 player? Well, the point of it is to give out sound so you can hear the song or podcast. So sound is our useful energy in the MP3 player. How does our energy get wasted in the MP3 player? Well, if it's been on for a while, then it's going to get warm. So heat is often a very common wasted form of energy. So I'm going to give you 4 more devices, and I'd like you to write down what forms of energy are useful and what forms are wasted. So our first one is a TV. What energy is it giving out that is useful? Remember, there might be more than one type of energy that is useful in each case. Also, write down what the wasted energy in the TV is. I'd like you to do the same for the car as well. So if you need to pause the podcast while you're thinking about it, pause it as and when I give you each device. Third one, I'd like you to tell me the useful and wasted energy in a gas cooker. Finally, fourth example, in a light bulb, what are the useful and wasted forms of energy? So I'm going to tell you what the answers are now. In a TV, we've got 2 useful forms of energy. The TV gives out a picture and it also gives out sound. So the 2 useful forms of energy are of course light and sound. The wasted energy will be heat. If you've got a very large TV, particularly, if you put your hand on the back of it, or near the top, then you'll be able to feel some of that heat that's giving out. In our second example, the car, the useful form of energy is the energy which allows the car to get from A to B. This is movement, and so the useful energy is kinetic. Wasted energy is when the engine gets hot. Not all of that energy from combustion of the fuel is used in driving the wheels forward. So heat is a wasted energy. Can you think of a way in which that heat is turned from wasted into actually a useful form of energy in a car? It's in the heaters. So the heaters take air that has been run over the engine and been warmed up and then pipe that through into the car space to warm it up on a cold day. Number 3, the gas cooker. In this case, the useful energy is heat because we want to be able to cook our food by using thermal energy. Wasted energy is in two forms. The first one is also heat, because not all of the energy from the burning of the gas actually goes into cooking the food. Some of it will go to the surroundings. As you put your hand near a cooker, you'll feel the heat coming off it, so not all of that is used to cook the food. The second form of energy that's wasted is light, because the light doesn't actually do anything to help you cook the food, but of course you can see the flame, so that energy is not useful for the purposes of cooking food. 4. Light bulb. Our useful energy here is light, and our wasted energy is heat. For the picture of the bulb that I've shown in the video, which is an old style filament bulb, this is particularly inefficient at converting electrical energy into light energy. Typical filament light bulbs might give out about 10% light and 90% heat, which is a terrible waste of energy. So laws have actually been introduced in the European Union and in other countries where these filament bulbs are not allowed to be manufactured anymore. So you'll find new style energy saving light bulbs which waste a lot less heat and give out a lot more light. Now I'd like to talk you through Sankey diagrams. For Sankey diagrams, it'd be really useful to be able to watch the video in this case, or if you have a revision guide or a website open with a picture of a Sankey diagram, you'll be able to see what I'm talking about. A Sankey diagram consists of arrows. On the left hand side of the Sankey diagram, the width of the arrow represents the input energy. So taking the example of a light bulb, our input energy is electrical energy. The width of that arrow tells you exactly how much electrical energy is being transformed in that device. On the right hand side, there are two arrows, one pointing to the right, one pointing downward. The arrow pointing to the right is our useful output energy. The arrow pointing down is the wasted energy. In a light bulb, the wasted energy is thermal energy. By looking at the width of the arrows, you can tell exactly how much energy is wasted and used. So in the diagram on the left hand side, we have a very wide useful arrow and a very narrow wasted arrow. So this particular device is very efficient at turning the input energy into useful energy. On the right hand side, I've got a Sankey diagram where the output energy that is useful is quite narrow compared to the wider wasted energy arrow. This shows that the device is not efficient, as more energy is wasted than is used to do something useful. So to recap that, if a device gives out a lot of useful energy compared to wasted energy, we say the device is efficient or has good efficiency, and if inefficient or has poor efficiency. So as well as being able to give you a quick guide to how efficient the device is, you can actually measure the width of the arrow. Of power or energy are wasted and used in the device. So I'm now going to give you a couple of examples of Sankey diagrams, and I'd like you to work out what the missing number is in each case. You need to remember while you're calculating these that the law of conservation of energy tells us that the input energy is equal to the total output energy. So the amount of energy you put into a device will equal the amount of energy you get out of it. And the energy you get out of it is in two forms, wasted and useful. So example number 1, we've got 10 joules going into a device. 2 of those joules are wasted. So how many joules are useful? Example number 2. This time, instead of using the units of energy, I'm going to show you in terms of power. Power is measured in watts, and power is a measure of how much energy is being transferred each second. So the amount of power that is being put into this device is 800 watts, which means we're using 800 joules per second. We're getting 200 watts of useful power out of the device. So how many watts are wasted in this device? Now the final thing I'd like to do for each question is work out the percentage efficiency of each device. To work out the percentage efficiency, I'd like you to take the useful output energy, divide that by the total input energy, and then finally times that by 100, and that will give you a percentage. So have a go at calculating those two examples. Pause the podcast while you're doing that, and then check your answers in a few seconds. So in the first example, we had 10 joules of energy inputs into the device. We had 2 joules being wasted. So that means the difference of 8 joules must be useful. To work out the efficiency, you divide the useful energy divided by the input energy times by 100. So I take 8 joules, divide by 10 joules, times by 100 equals 80%. 80% efficiency is actually pretty good for a typical device. Second example, even though this is measured in power rather than energy, it's exactly the same calculation. 800 watts goes into the device, watts is useful, so again the difference of 600 watts is wasted. To calculate the efficiency, 200 watts divided by 800 watts times by 100 equals 25% efficiency. 25% efficiency is a little bit more realistic for certain things like motors in cars. So that just about wraps that up. If you've not been watching the video or not had a revision guide in front of you, then I really encourage you to have a look on the revision link that I've given you at the end of this podcast, and have a look at some Sankey diagrams, and then try some more calculations using the quiz link or using a revision guide and finding some example questions of yourself. Have a go at working out how much energy is useful or wasted in different devices, and also have a go at calculating the efficiency of those devices. So as a final recap, there are 9 forms of energy. You can only transfer energy from one form into another. Energy cannot be created, it cannot be destroyed. You can only have the same total energy at the beginning as you do at the end. Energy is transferred from one form into another, or from one form into several others. You can calculate the output energy or wasted energy by working out the difference of one of those from the input energy. You can work out the input energy by adding up the useful energy and the wasted energy, and you can calculate the efficiency of a device by dividing the useful energy by the input energy and timesing by 100 to turn that into a percentage. Well, thank you for listening to episode 3 of Physicasts in year 10. Next episode, in episode 4, we'll be looking at how you can work out, how you can calculate how much it costs you to run a heater for 6 hours. How much it costs you to play your PlayStation, how much it costs you to run a light bulb for a year. This podcast was an episode of Physicasts, physics podcasts for 14 to 19 year olds. Physicasts is written and produced by Tino Race. You can find out more about Physicasts on our website www.physicasts.co.uk.